I guess we're still missing Lorena, but let's we can start. So last time we managed to do two things. So we managed to define the Cartier operator. So, well, in principle, there is one for E equals 1, and then its iteration gives you all the other ones. So they took us a while, right, because we had to define omega r. And so we know that omega r only exists if r is finite over what? Over a Gorenstein algebra. Over G, that is Gorenstein, and the dimension of G is finite. We also need R to be equidimensional for this. But these are very, very mild hypotheses. So that took us a while, right? Like it took us a lot of things that we had to learn. Gorenstein rings, Cohen-Macaulay modules. We had to rely on Grothendieck duality and a whole bunch of things. So it is quite of an accomplishment, right, to get to define this. And so we also saw that this object is better understood for Cohen-Macaulay rings. Actually, Cohen-Macaulay rings are, engineered so that you can understand this very well thanks to the duality. Right, so we saw that, and the point today is that, or probably this week, is that this is not a final form. The best way to look at this is to look at this on normal rings. So we're going to see that what I want to cook up is a canonical divisor. So I want to write this like this, where this is a canonical divisor. And this illustrates that whatever omega r is on normal rings, it becomes a reflexive module, a reflexive sheaf. And so this is going to look like this. And this is going to be wonderful because thanks to this abstract reflexification process, you can do a whole bunch of, you can massage this map and write it down in a whole bunch of ways. For example, we will see that this map is essentially equivalent to the following. So I can take this part and move it to the other side. Like I can restrict what the codomain is by enlarging what the domain is. Sorry, by restricting what the domain is. So there is a formal process to do that. And this is this. And for example, we'll see that this will be isomorphic to this, thanks to all this. And in particular, what this is telling you is that any other map here, and its evaluation at 1, the trace, can be understood through the Cartier operator. Okay? So that's the goal. The goal is to enrich the Cartier operator on normal rings so that any other potential splitting for the ring can be understood through it. Okay? And so to do that, we're going to have to learn a whole bunch of new things. In particular, the theory of normal rings and divisors, which I think we have to. It's a little bit of preliminaries, but we have to do that if we really want to have a very good understanding of the theory. So let's do that. That's the new section 5.5. I call it normal rings, divisors, and what we're looking for in the canonical class. I should say the canonical divisor class. Let me say it like that. And the other wonderful thing about this is that it's going to make the connection with birational geometry very explicit. So okay, let's get into that. So reminder, it's an exercise. I think I let you do that as an exercise a while ago. But let's recall what this is. So let's take R, any ring. And so how do you understand reducedness? Well, we know that by definition, this means that there are no nilpotents, no non-zero nilpotents. In positive characteristic, we can further understand this by saying that the Frobenius is injective. But there is a cool way to understand it. This is the grown-up version of reducedness. This means two things. This means R0 plus S1. So R0 means that Rp is regular if the height of P is 0, and this 0 is this 0 here. Okay? So if you look at the minimal primes and you localize a band, you get a regular ring. Okay, for example, if R is integral, this means that this thing is it's a zero-dimensional covariant ring. Zero-dimensional regular ring. Therefore, a field. Okay, and so the S1 tells you that, well, technically speaking, I should write that the depth. Now that we understand what the depth is, the depth of R localized at P is bigger than 1, and this 1 is 1 here, and the dimension, let's say the height of P, which you know is the dimension of Rp. So what is this condition telling you? This condition is telling you that if the height of P is 0 or 1, i.e. less than 1, then the ring Rp is cohomological. But if the height is higher than 1, like it's 2, 3, 4, 5, and so on, then at the very least, you know that the depth is 1 or more. Okay? So that's the way to understand this condition. This condition tells you that in very low codimension, for dimension 0, 1, you have cohomological coordinates, and away from that range, at the very least, you know that the depth is more than 1. Okay? This is the so-called third first condition. Okay? So this is the kindergarten condition or way to understand reducedness, and this is the grown-up way. So probably if you ask Rosen what reducedness means, it's going to tell you this exactly. This is the EDA way, so way to understand this. It looks very abstract, but it's very useful especially because it gives you a homological way to understand it. As we're about to see, as well, it's right there, right? It's a depth condition, therefore it's a homological condition. You know Grothendieck's philosophy, right? Everything has to be cohomology. And so that's why this is good, because reducedness becomes some cohomological property. And so, well, let's give the general definitions then. So definition. So let's take a ring R, and so what else? Let's take K to be some integer. So the first definition is the following: R. What I just want to say satisfies the condition Rk. So usually this is a bold phase R, but I cannot do that here. If, or you also say that R is Rk, or R has Rk. If and only if Rp is regular for all P such that the height of P is less than K, less than or equal to K. So it tells you that in the small codimension relative to K, you have regularity. So the singular locus gets very, very small. Okay? So we also have GK, actually. I think it's going to be useful. GK, and it's the same thing. But instead of regular, what do you think you put here? You put Gorenstein. You also will hear people saying that this condition is equivalent to R being regular if I dimension K. Because that's what it means. It's just an interpretation of that. And we say that R satisfies the condition Sk. This is the so-called Serre's K condition. If and only if when you look at the depth, actually this can be done for any module. So let me put a module here. Sorry. And so let's take M to be let's take it to be a finally generated R module. Because we're going to talk about its dimension and support and so on. So let's take a module like that. We say that it satisfies this K, if and only if, when we look at the depth of MP over RT, okay, then it is at least, right? It tells you we want the depth to be big, right? This gives you a lower bound of what the depth is. It's a good condition. So it is, more than the minimum. In other words, it's bigger than both. No, sorry, it's bigger than, yeah, the smaller one, sorry. So the minimum of K and the height, let me just put it like this, the height of P. Okay, so for example, if we put n equals r here, this tells you that if the codimension is less than k at a point, then it is cohomogous. But if it's not that, then at the very least the depth is bigger than k. Maybe not cohomogous, but at least the depth is bigger than that. So exercise. Just a few remarks that you can do as an exercise. Well, first, R is regular. Let's say respectively Gorenstein, respectively Cohen-Macaulay, if and only if R has or satisfies RK, GK, SK for all K. B, I guess, R satisfies S1 if and only if R has no embedded points. So the S1 condition is very down to earth in a sense, right? So let's move on here. The S2 condition is very down to earth too. So C, let's just put R as S2 if and only if you take any principal ideal, this has no embedded points. And of course, embedded primes are not. So it's very down to earth to write. Actually, if you put here r equals 0, it's just as 1. Right? So S2 has to imply as 1. Right? They get bigger. Sorry, they get better. And so when you put r equals 0 here, you get the 0 ideal. And so saying that the 0 ideal has some embedded primes is the same thing as S1. So S2 is an improvement on that, in which you now consider principal ideals.
Are there means that a principal ideal, or what's this notation?
Principal ideal, the principal ideal generated by R. So yeah.
Okay.
So it's the ideal generated by one single element.
Is it for every R?
For every R.
Okay.
If it is a zero divisor, then it's an S1 condition. But when it is not a zero divisor, maybe that's the question you have. That is like the new improvement. Because then the height of this idea is divided by the rules and so on. So, and I can tell you what SK means. D R is SK. This one is a bit more complicated. If and only if so when you look at, let's say for all ideal A, so what you're looking for is ideals A generated by height of A elements. Okay? For every ideal that is generated by a number generated that coincide with its height, well, and this height of A is less than k minus 1, okay? Then A has no embedded primes. And this goes by the name to say that A is a mix. In particular, A is a mix. We don't need this actually. I'm just saying this. We're gonna need this. This one is very useful. This one not so much, but I want to put it here for context, historical context, because there was this very famous unmixed theorem, I guess in the 50s, 60s, around those decades, in which people would say that what the unmixed theorem was that, for a ring was that if you have any ideal like this that is generated by height of A elements, then it is unmixed. Okay? And that was a property that the polynomial ring has, and actually Macaulay himself proved that. So what he did was secretly to prove that the polynomial ring is Macaulay, and therefore it has the unmixed property. And so as a corollary, you see that R is Macaulay if and only if, but people will say the unmixed theorem holds on R. So let's say R has the unmixed property. Meaning that if A is generated by height of A elements, R, then A is unmixed. The property of being unmixed means two things. It means that it has no associated primes, and that the minimal primes that you have, the associated primes, they all have the same height. So it is equidimensional. If you think about what if you do geometrically, it means that every reducible component of the variety cut out by A has the same dimension, but also there are no embedded components. Okay? And so this is a property that is wonderful, and people were trying to prove it for polynomial rings, and Macaulay did just that. The same Macaulay of Macaulay. But now we understand that as saying that, oh, the polynomial ring is Macaulay, therefore it has a property.
Right, we also need all the minimal primes on the same height, but with at least one and the shared prime. We'll say that that is Dimensional.
Equidimensional, yes, exactly. So omega means equidimensional and no embedded primes. So it's stronger than equidimensional. Exactly.
Last class you said that this condition, the R having no embedded primes could be stated in terms of local homology as the first vanishing?
Yeah, because it means S1.
Okay.
Literally S1, and S1 is a local homology property. It's the vanishing of the first local homology module. Yeah. So that's the brilliant of all this, that all these properties that I write on the right hand side are deep down homological properties. They have to do with the vanishing of local homology. That's a wonderful thing about it. And it gives an interpretation of what local homology means. Okay?
Is here R is a local ring or not necessarily?
Yes and no. So yeah, so when I say this, it means that this happens like locally. It's a local condition. And so the point is like both sides are local properties. So you can check.
I mean, all from the beginning you were assuming R is a local ring or no?
No. Yeah. However, I may have done that because that's the important case anyways. Because you can always reduce to the local case. So. Yeah, so this is important to know because also it gives you a taste of what cohomology means. It's just nothing mysterious. It's just that it's this mixed property if you want to think about it. And those terms. So next, so I'm gonna give you a list of exercises. That I need you to do. So the first exercise is the following. We're going to take R, a ring that has a canonical module. Okay? So meaning what I started to say today, like R is finite or recurrent in algebra, blah, blah, blah. Okay? Let's just assume that R admits a canonical module. Yeah, so the first thing I want you to prove is that omega R satisfies S1. Okay? Yeah. So I give you the hint in the notes, but well, let me say what the hint is and just in words. So the zero-dimensional case is kind of trivial. So the idea is that you reduce the positive dimensional case. And when I say positive dimension, there should be a light bulb, lighting up. What would we do when we have a positive dimensional local ring? Well, you reduce the local case too. We can cook up a regular element, right? That gives an exact sequence, right? And remember, R times multiplication by that regular element, and we take the quotient. And once we have a regular sequence, we can look at what happened to the depth, because the depth is cohomological. Therefore, there will be non-exact sequence and local cohomology, and so on. And when you think about what that means in this case, and what omega R is, and how it deforms, because it is actually, like, you have to assume that well, the omega R is literally this X too. How was that? G or no? R G G, right? And so you can also explore what it is through this exact sequence. Okay? And so then you conclude that omega R has to be S1. I'll let you do that. So now if R is further S1, in other words, R has no embedded primes, then omega R is also or satisfies the S2 condition. Okay? That's the key. That's the key of this whole business. I guess we'll see the full power of this on Thursday. That's going to be the key to cook up the canonical class. And the proof is the same trick. Okay? So there are more exercises here. And the last exercise, well, there's an intermediate one, but it's used as a lemma to prove this following, this other one. So take R as before. So in other words, R with canonical module, and assume that R is S1. In other words, R has no embedded primes. And what we need to do is to consider the following canonical map. This is something that is true for the dualizing complex that we were mentioning the other day. That this is an isomorphism, and we want to bring it down to the level of modules. So we have this canonical map, right? What is this map? It's the only thing you can do. You take M, and you have to send it to a map that sends a map to an element of omega R, right? So let me take a map here. Let me call it mu. Right, mu belongs here. So you have to send it somewhere in here. So where exactly? Well, this is going to go to mu evaluated at M. Okay? Because mu of M is an element of omega R. It's just evaluation of M. Okay? So there is this canonical map. So what you can see we're doing here, we're taking a sort of double dual, but we dualize with respect to omega. Omega has good dualizing properties. That's why we like it, right? So, and we want this to be an isomorphism, okay? So this happens. This is an isomorphism if and only if, and this is the important punchline, M is S2. So this is going to be an exercise for you. I'm gonna so here in the notes you will see a big hint on how this works. Okay, but it's not terribly hard. And so, but what is the philosophy? The philosophy is that there exists a dualizing complex from which this is just a cohomology, right? You remember we were talking about it? That dualizing complex, by definition, has this property in certain derived category. Okay? And then what you want is to bring that down to the category of modules. But how do you guarantee that? Cohen-Macaulay. Okay? That's the principle. Cohen-Macaulay property, here you have an S2, is that property that lets you collapse that property on the derived category to the category of modules. By design. Okay? So you have this in particular. If we plug in here n equals r, what happens? This module here collapses to simply omega r, right? And so in particular, the canonical map that goes from here to here, that sends simply r and 2 multiplication by R, right? In other words, you send 1 to the identity, right? This map is an isomorphism if and only if R is S2. And that's why the S2 property matters, believe it or not, because it tells you this wonderful property about omega R. In particular, if you apply, let's say B, if you apply Dollery to this, you see that you get an understanding of what the top local homology of omega is. It's an injective fold equals an injective fold of the residue field of P. So I think the other day I mentioned this property, right? But I didn't put the S2 condition, and so I think I made a mistake. I think you need S2 for this to be true. Because the only proof I know of this is by using duality and the fact that this Hom set here is equal to R. However, I've seen this claim without assuming that R is not S2, I think. And so I think there is a chance that it may still be true without having to assume that R is S2, but I'm not sure and I don't believe it. I think the reference I was using may be wrong, but I need to double check myself on that. But at the very least, you can be confident. Okay, you can bet your life that this cohomology module is injected for the residue field if R is S2. Okay? Which is a very mild hypothesis. More often than not, this is usually the case where R is cohomology, so super safe. Okay? But this is going to be important because it gives us the following property, whose proof is going to be an exercise too. And I guess you already know my philosophy. The only way to learn all this material is by doing the exercises yourself. I may be a bit biased, of course. I just find reading proofs boring. I don't know if it's the same for you. I like maybe trying to think about them myself. So what I'm doing is to break down the theory into a whole bunch of exercises for you to really choose the important points. And so out of this, actually, so actually this operation here, you will see because of this in the literature, this is called the S2ification. So the point is that you have a module and you want that module to be S2. And so you put it inside a bigger module. Actually, this is easily injected, you will see. And what this does is to give you the S2ification of your module. This module is S2 actually. And out of that, we get the following. I put it here as a proposition. And this is why the S2 property matters. Suppose that you have a morphism of modules. So our modules map. Okay? Suppose that M and N are S2. Okay? Then P is injective, respectively, surjective, respectively, an isomorphism, if and only if phi P, the localization of phi at P is so, respectively, for all P. And in principle, oh, sorry, people on Zoom. I'm so sorry, forgot to move it. give you a few seconds to read it. So we were saying that if you have any manifold modules, and if both modules here are S2, and if you want to prove that phi is injective, surjective, or an isomorphism, well, you know that you can do that locally, right? You can do that locally at every P. But if M and S are S2, you only have to do it generically, in other words, at the height 0 points, and at the height ones, and at the height 2, which is a crazy simplification of this. If and only if this is true, for all P, of height, actually, yeah, of height, like this. Actually, there's a type here. Here row 2, but it should be 1. Isn't that absolutely crazy?
Does that generalizes for SK? Like height being less or equal than k minus 1? Or?
I don't know. I don't think so. I think it is because it really has to do with a vanishing of the first cohomology thing. So the way to think about this is that what you want to do is to lift a certain section when you restrict to an open. And the obstruction is certain one of H1, U, OU, like the Coherent cohomology. And that H1 becomes H2. And so it is the obstruction to lift sections. You know, like if you have a short exact sequence of modules and you write down, you apply the section, the functor of sections, you want to lift that. The obstruction is an H2. But it's a very specific interpretation of H2 or equivalently H1 for coherent homology of an open subset. So that's what is happening here. Okay. Or because it has to do with this interpretation. So it's that. It's that. So I don't think there is such a generalization, at least that I know of. It is this thing, you know, like so think about, so you know, like the homology is did down in some X functor, right? And you think about X, you have a very good interpretation of what X1 is. It's extensions of modules. But tell me what X2 is. X3, X4. I think that's the principle behind this. Okay. But you're free to think about it, and if you can come up with a nice generalization, it would be wonderful. But I don't know of any, and I'm not optimistic that one could find one.
But it will be like very weird because it's like as I get a higher SK, the condition gets like more complicated because I'm checking more primes instead of lesser primes, because now I'm considering primes of bigger heights.
Yeah.
So the condition is getting like, instead of being a more helpful criteria, it's getting a more complicated criteria.
If you increase K.
Because on the right side,
oh yeah, I see what you're
increasing the amount of primes that I need to check.
Yeah, I see your point. Yeah, it would be a weird thing too, right? Because if you increase K here, this becomes a stronger condition,
yeah,
but this will become weaker.
Yeah.
So yeah, it would be weird too.
Not work.
Yeah. Okay, so that's it about the S2 property and its nature. And let me tell you why Sir came up with it. This one reason. Okay, definition. If you have a ring, here is normal. Remember, we always assume rings to be Noetherian. So a ring R is normal if and only if it's a local property. So the property is that Rp is a integrally closed integral domain. For OP. What is the meaning of this? Well, this means that this ring is a domain, integral domain, and so it has a field of fraction, right? And actually, this field of fractions, well, it has a field of fractions. Well, it will be essentially the field of fraction of R if R were a domain, but it has a field of fraction, and so we can look at the integral closure of Rp inside here, right? And so integrally closed means that the canonical inclusion is just equality. Okay? You have seen this before in computer calculation. It's a standard thing to do. Probably in a just a basic algebra course. Okay. So actually remark / exercise. It is an exercise in the notes. If you have a normal ring, if R is normal, then it breaks down, essentially because it is well, yeah. It's an exercise. It's gonna break down as a product. How many? N. As a product of rings where these are normal integral domains. And one can see that a domain, an integral domain is normal if and only if it is integrally closed, because then you check that at the generic point. So yeah. In other words, when you're studying normal rings, you often can reduce to the integral case. Okay? This phenomenon here is actually a general thing that so the point is when you have a normal condition, irreducible components coincide with connected components. So if you look at a normal ring, and you look at, so the point is that when you look at a ring and you look at the irreducible components, and you look at where they intersect, that point there cannot be a normal point. Normality rules out that you cannot have those intersections. For example, you can take the ring, which is just the axis, you know, and it's not normal here. Normality rules out irreducible components intersecting. Okay? Just keep that in mind. Normal means, well, it doesn't mean that, but it implies that irreducible components are the same as connected components. So that's the principle here. And therefore, when you study normal thing, you can just reduce to every single component. Just be happy. Okay? So here is the search theorem. Search criterion for normality, and it says that normal equals R1 plus S2. You remember reduce was R0 plus S1. So you just increase the parameter here by 1, and you get a wonderful notion of normality. And we are going to explode that, both of them actually, in a fundamental way to our paper. But S2 already we can see that it implies wonderful things. And the R1 is going to imply a whole bunch of other wonderful things. Actually, we will see another weakening. So first, we're going to use a weakening that is the so-called G1 plus S2. Okay? this is the natural setup to talk about divisors. It's just designed for that. But we'll see that if we improve from Gaussian to regular, we have a whole bunch of other nice things. The reason is that we want to localize the point of the dimension one, a prime divisor, and cook out evaluation ring out of that, and that's the R1 hypothesis. But for now, we can just reduce to this. You see this a lot in the literature actually. But geometers just like to stick to this. They don't see too much of the value of using coordination instead of regular. So a nice corollary of this is that if the dimension of R is less than 1, I guess 1, then regular equals normal. So you see that if you have a curve, for example, and you take the normalization, then it becomes regular. So the general principle, that's how you can desingularize curves. Just taking the normalization. Another consequence you have is that if you're looking at surfaces, then normal implies plasmacology. So you see that a lot. Like a normal surface, people often get. You see using the plasmacology property a lot. What time is it? Any questions so far? Now, what I want to tell you is why normal rings are wonderful. We're almost there. Okay, normal rings are S2 plus this other property. So reflexification. I told you about S2ification, and the point is that on a normal ring, S2ification and reflexification are the same thing. So let's look at that. So let's take a ring R, and out of this ring, we can cook up a functor that I'm going to denote like this little bird here. And so this is by definition the functor given by homing into R. So it seems like a very reasonable thing to do. And it has an actual transformation. Well, when you apply the double dual, let's call it alpha. And so what is alpha? Alpha m could be something like this. You dualize it twice. You take the first dual, and then you take the second dual. And for example, from linear algebra, you learn that this is a field that this is an isomorphism. What is the canonical map? We already wrote it down, right? Like so, it's you set M and you send it to evaluation at N, which is the map that takes a mu and simply evaluated at n. So this is alpha m, and this is a natural transformation. Meaning that this morphism here is natural on n. Okay? And you would love for this to be an isomorphism. And we already can understand very well when this is the case. Make a guess. Well, let me continue with the definition. So, yeah, this is called the reflexification. It's called reflexification. Because this is reflexive. And N is said to be reflexive if, what do you think? Alpha M is an isomorphism. By the way, we only consider finally generated modules here, okay? So, I mean, the definition doesn't need that, but let's impose it. Only for finally generated modules, okay? So a module is, if a module is reflexive by definition, it is finally generated to start with. Is everyone happy with this? And now, as it should be, we're ready to prove something that actually could be hard to prove if you don't do it the right way, which is what we just did today. So, theorem or proposition, or you want to call it. Suppose that R is actually, all I need is that it is G1 plus S2. In particular, normal. Then M is reflexive if and only if M is. What is the consequence here? What is happening? Why the G1? What is the difference between reflexification and acidification? What is the difference between this functor and the one we considered before? That before we had omega. Omega is the one with good dualizing properties. But if I put here G1, it's because omega coincides with R in condition 1. So that's what the G1 property is. So this is reflexive if and only if M is S2. What is the proof? M is S2 if and only if, let's say, is reflexive when you dualize with respect to omega. But G1 means that it's the same as dualizing with respect to R in the small codimension, which is what matters. So that's it. This is the punchline for normal rings. When a normal ring, reflexification, well, being reflexive and being S2 are the exact same thing. That's it. But for this, we will have just put G1 plus S2. So the R1 hypothesis is going to come up later, for sure. But this is the first thing we need for normal rings. On normal rings, reflexive and S2 are the same thing. Just put that in your head. On a normal ring, reflexive and S2, exact same thing. Okay? And believe me, we're gonna do that a lot. So That's not my notes. Okay, we're here, 36, now 37. Okay. And so in practice, so when we work with normal rings, in practice, what this means is that we are going to be proving things in very slow dimension if we are playing with reflexive modules. And we will see that reflexive modules are easy to cook up. They are not weird. Sorry, they're not rare. Okay? Or more geometrically speaking, what people do is that, like you can say, okay, when I'm working on a normal ring, I'm going to prove things on the regular locus where things are wonderful, and then all I have to do is to reflexify. And that's a very important trick. Okay, and algebraic geometry just in general. Actually, I have all these memories of being stuck with a lot of problems that I deemed very, very hard. And I went to my advisor for help. And very often his answer was like, have you reflexified? And I was, of course. And so it's a very important trick. On normal rings, you can just prove things in the locus where they are true, and then you reflexify and you get it extended. So, yeah. Now, next ingredient, that's for normal rings for now. Let's talk about divisors. Divisors, we'll see, are the computational counterpart of reflexive modules. They are a bookkeeping tool. Okay? We'll see what they are. So, first of all, we are going to take R from now on to be a normal. I'm going to take it to be an integral domain. I don't see the point to consider more general rings. For this, I want to have a fraction field over there to play with. So A prime divisor let's call it P, capital P, is by definition just a closed subset or closed override or closed subscheme, whatever you want to call it, cut out by a prime ideal. Okay? Where all I want you to have is that the height of P is 1. So you can see that on a normal ring, if we play with reflexive things, which are S2, we only have to care about the generic point for dimension 0, and the next height 1, prime divisors. On a normal ring, that's the whole point. The primes that seem to know everything about the variety, let's say, are the generic point and the prime divisors. Look, a prime divisor is just its by definition essentially the data of a prime ideal of height 1. Height 0 means the 0 ideal, unless you go to the next level. And on normal rings, essentially that's all you have to know. Okay? Because of this. And you want to keep track of what's happening in dimension 1. So that's going to be the formalism of divisor. So prime divisor is going to be the first thing, okay? Again, the prime divisor, just based on the definition, is just that. It's just a prime ideal of height 1. But it's very important, or it's I don't know, it's convenient to think about the closed subscheme cut out by that P. Okay? So we're going to stick to the geometric formulations. a Bell divisor? Well, first of all, let's say we're going to define this group, the group of Bell divisors of R. And this is by definition the free abelian group generated by prime divisors. Any set in the world generates a free abelian group, right? Particularly the set of prime divisors. And that's the group of divisors. So an element here, D, what is an element here? Well, an element here is a formal sum, it's finite, right? It's a formal sum over P such that, well, AP is an integer, and what, P is a prime divisor. And all, but finally many, AP are 0. By definition of free abelian group generated by a set. So think of a divisor, and so this is by definition a divisor. Well, technically speaking, it's a Bell divisor. But I never say Bell, so let's just say a divisor. So think of a divisor as the record of multiplicities at every single prime divisor. That's the bookkeeping I'm telling you, I'm talking about here. So you go through every single prime divisor in your variety, and at every single one of them you record some number, and you keep it there for the record. Okay? And that's going to be very convenient because that data is important data. That's the point. But then like, you're going to want to manipulate that data. But that's going to be equivalent to doing arithmetic over Z, adding numbers, and that's easy. Okay? So think of divisors as your friends. I'm saying this because very often community algebraists don't feel very comfortable talking about divisors, but I don't see why. Think of them as your friends. They're good things. They are simplifications of what you want to do. What else? Often we write a P to be the evaluation of your divisor at P, or the order of vanishing of D along that specific prime divisor. What is next? C. D is effective, and you write D bigger than 0 if the evaluation of D at every prime divisor is non-negative. Later on, we're going to be talking about A divisors. When A, well, in principle it can be any ring, but let's say we're going to care about Q divisors, Z localized at P divisors, but you can talk about PI divisors, you can talk about R divisors, and any ring you want. And what is that? Well, it's an element of what people denote by D, A, R, and you just enlarge your coefficient. You just take A times or Z divisors. Okay? So what is that? It's just a formal sum of prime divisors, but now the coefficients belong to the ring you want. And we'll see at least in this course that Q divisors and ZP divisors are very important. Okay, any questions? Now, we're going to see the first example of recording information in a divisor. So, Now, this is where we need the R1 hypothesis. Where is that? It's over here. Now, remember, normal equals R1 plus S2. Now we're going to use this property here. So what does that mean in practice? It means that if I take R and I localize it at the prime divisor, meaning that I localize it at P, where P is the variety of P, okay? This is regular. It's a regular one-dimensional ring. Therefore, it is what? It is a discrete valuation ring. Remember, regular in dimension 1 means DVR. Okay, so this is a DVR. That's the second important property about normal rings. When you localize at the prime divisor, what you get is a DVR. Therefore, automatically you have evaluation at P. What is this? This is a map from units of the field of fraction. So let's say K. Let's say K is the field of fractions of R, which is R localized at the prime ideal of height 0. So this goes to Z. Okay? In other words, you take a function that you should be thinking of as a metamorphic function on your variety, and you can cook up what is the order of vanishing of that function at F. If it is positive, it is because it vanishes along that prime divisor at a certain order. If it is negative, it's because it has a pole along that divisor of certain order. If it is 0, it's because it is a unit along that divisor. It's not a pole, it has no zeros, no poles. Okay? And so that gives us a wonderful map. Let me write it down here. I guess this map is an exercise too. So we're going to have K, and then we're going to have a map to divisors. Okay. So we're going to take a metamorphic function, and we're going to define the divisor of this metamorphic function. I'm going to call it div. So this map here is going to be called div. And so what is the divisor of a metamorphic function? You simply do the bookkeeping, you do record of the evaluations of this function at every single P. So the divisor of a metamorphic function is just the record of zeros and poles of that function with the respective orders. Okay? Well, the first is to prove that this is finite. Exercise, prove that this is finite. It's not difficult. A function cannot vanish at infinitely many times or have infinitely many poles. And the other thing that I'm going to leave as an exercise is that div is a homomorphism, it's a group homomorphism of abelian groups. Well, this follows from the properties of evaluation. You know, the evaluation of the product of functions is the sum of functions and so on. What do you think is the kernel? What is a meromorphic function that has no zeros, no poles? It has to be a unit of R. Okay. So, well, this is how you prove this. Actually, you're breaking down in two parts. So the divisor of F is effective if and only if F is a regular element. And well, yeah, so the and the divisor of F is 0 if and only if F is a unit, it vanishes nowhere. It belongs to no maximal ideal. Okay? So the kernel of div is the group of units of the ring. And the co-kernel is by definition the divisor class group. Okay, so this thing here is by definition, I'm defining, okay, it's the co-kernel of the map. By definition, is the divisor class group. Which is a very important object in the history of algebra. Actually, it was trying to define it, what made ring theory possible. You know, like to try to define what that was, people invented ring theory because people noticed that the divisor class group was an obstruction to solving things like Fermat's theorem and so on. And when today it's a very important invariant of singularities. So, what else do we need to say about it? Well, more terminology, I suppose. These divisors here, so the image of div, let me write it down here. The image of div are the so-called principal divisors. And the divisor class group is simply veil divisors modulo principal divisors. So for example, you say that two divisors are linearly equivalent. D1 is linearly equivalent to D2 if and only if the difference is principal. And it is this equivalence relation what you impose on div to get a divisor class group. Okay, you simply identify divisors of two linear equivalents.
What's the definition of the divisor class group?
Yes, it's a definition. The definition of the divisor class group is as the co-kernel of this map. So it's div modulo principal divisors. Veil modulo principal is the divisor class group. And what it does is to measure factoriality. So it is an exercise just for you to get some taste of what it means. You can prove that it's not difficult that R is a UFD, unique factorization domain, also known as factorial. I prefer this name, this is the French name, I think, factorial. If and only if the divisor class group is trivial. So you can see that the ring has trivial divisor class group if and only if it is a unique factorization domain. And historically, this is the property people were trying to understand. Very back in the day, like Kummer, Kroll, all these people. And this is the neat way to understand it, just by a group. Which was like what people were trying to understand, you know, like groups, rings, these sort of properties. But you can see, for example, like how it breaks. For example, if you have this ring, take any field that it has characteristics different than 2. So let's try to break unique factorization. That's an easy way to break unique factorization. Here you have two elements with different factorizations, right? You have x times y and z squared. And you can see that this is z mod 2. And the 2 has to do with this. If you put n here, you get z mod n. This is something you can try as an exercise. It's not difficult. What is another way to break unique factorization? You can take 4 variables and say that x times y equals c times w. That's another way to do it. And when you do that, you get a divisor class group, which is isomorphic to z. In fact, the generator is like x times x comma z, and so on. So that's what the divisor class group is trying to tell you. Okay.
The notation for the divisor class group is an A or a CL?
CL.
Okay.
Yeah, sorry about that. I think we're almost done for today. So let's see what. Yeah, now let's make the connection between these two things. So what is the whole connection? So take D to be a divisor on a normal integral domain, okay? Out of this, we're going to define a reflexive module of rank 1. So this is going to be, by definition, all the metamorphic functions, okay, such that the principal divisor of f plus d is effective. So you can think here, you are saying here that you're prescribing metamorphic functions. That's the algebraic way to do it, you know, like with prescribed poles and zeros. You're going to look at that. Okay. Well, here I forgot to add a 0, so I have to add the 0 artificially, or what I can do is to say the divisor of 0 is infinity, and infinity plus d, yeah, or I just add it like that. And so notice that this is an R submodule of K, so this is an R submodule. Okay, of rank 1. So, well, this module here has two properties. First of all, it has rank 1. So it's a rank 1. Rank 1 means that when I go in tensor with K, the field of fractions, I get a vector space over K of dimension 1. And it is reflexive. It is S2. And that should be intuitive because this object here is recording the information of a divisor, and the information a divisor records is dimension 1 information. What we're going to see next time is the converse. Any reflexive rank 1 module over a normal ring is isomorphic to RD. In other words, I can take any reflexive module and just write down the important information about it using a divisor. Okay? So this is the conceptual part, and this is the computational part. But since we're mathematicians, we want to be between both. You know, like we want to express our ideas over here, but when it is time to do computations, i.e. doing proofs, we want to be here. So that's the balance. Okay? And on normal rings, all this is possible. That's a punchline. Because on normal rings, reflexive is S2, and you know, notice that normality is used heavily to define this object, right? It's this. The R1 property is right here to define this, that. Okay. So that's what we're going to do next time, and we're going to use this formalism to to redefine the canonical module of normal rings. That's it. And once we do that, I promise we are ready to start doing F-singularities seriously. Okay. But we need all this background first.
Condition of the device for being effective over there, whether the element is in R or what is the element being removed.
What is the question again?
The condition, the device for effect
Has effective?
is the same as the element being an element of R.
Yes.
Oh yeah, because it's an element of K, right?
Yes, it's always an element of K. And so actually, that's the beauty of it. That's the beauty for normal rings right here, actually. The point is that on a normal, you can understand the elements of a normal ring as those elements of K whose divisors are effective. That's a very intrinsic property of normal rings. Another way to think about it is a property that you see for normal rings, saying that a normal ring is obtained as the intersection of the localizations at all prime divisors. That's another key property of normal rings that we're using here. We need to stop this.